Vera Rubin discovery. In the grand theater of the cosmos, the laws of physics were thought to be well-rehearsed actors. By the 1970s, we had a script, a narrative written by giants like Newton and Einstein that told us how the universe should behave. We understood gravity. We could predict the elegant waltz of planets around a star. It was a comfortable, predictable model. A planet closer to the Sun, like Mercury, orbits at a blistering speed, while a distant planet like Neptune plods along in its vast, slow journey. This is called a Keplerian decline. The farther you get from the central mass, the slower you move. It's intuitive, it's logical, and everyone, absolutely everyone, believed that galaxies, those magnificent star cities, should follow the exact same script. The vast majority of a galaxy's light, and therefore its assumed mass, is concentrated in its bright central bulge. So, common sense and a century of physics dictated that stars on the outer fringes of a galaxy, far from that central mass, should be moving slowly, barely hanging on by a gravitational thread. If they moved too fast, they should be flung off into the cold, empty darkness of intergalactic space, like a child letting go of a merry-go-round spinning too quickly. This was not a guess. It was a fundamental prediction of our understanding of the universe. Enter Vera Rubin. An astronomer with a lifelong fascination for the grand-scale dynamics of galaxies, she wasn't one to simply accept the established script. She wanted to read the stage directions herself. Working alongside her colleague, instrument maker Kent Ford, she gained access to a new, highly advanced piece of technology, the image tube spectrograph. This device was incredibly sensitive, capable of measuring the faint light from the distant, dim stars at the very edges of galaxies with unprecedented precision. A spectrograph works by breaking light down into its constituent colors, its spectrum. Within that spectrum are dark lines, absorption lines, which act like cosmic barcodes, telling us what an object is made of. But crucially, these lines also shift. If a star is moving towards us, its light is compressed, shifting towards the blue end of the spectrum. If it's moving away, its light is stretched, shifting towards the red. This is the Doppler effect, the same principle that makes a siren change pitch as it passes you. By meticulously measuring this red shift and blue shift across the entire face of a galaxy, Rubin could create a detailed map of its rotation, a galactic velocity curve. Her target was the Andromeda galaxy, our closest spiral neighbor. Night after painstaking night at the Kitt Peak and Lowell observatories, she and Ford pointed their telescope, gathering photons that had traveled for 2.5 million years to reach them. They were mapping the speeds of stars, moving from the bright, crowded center outwards to the sparse, barely visible edges. The initial data began to trickle in, and it made no sense. It was wrong. The numbers had to be wrong. According to the script, the rotation curve should have been a steep climb near the center, followed by a graceful, predictable decline as they measured farther out. But that's not what she saw. The curve climbed as expected, but then it just stayed flat. Stars far from the center were moving just as fast as those closer in. This wasn't a minor discrepancy. It was a flagrant violation of the laws of gravity as they were known. Imagine a solar system where Pluto was orbiting the Sun at the same speed as Mercury. It's an impossibility. The Sun's gravity simply isn't strong enough to hold on to a distant object moving that fast. The Andromeda galaxy was behaving as if Pluto was moving at the speed of a rocket, yet remained perfectly in its orbit. Rubin was a meticulous, careful scientist. Her first instinct was that there had to be an error in their equipment, their calculations, their entire method. They checked and rechecked everything. They calibrated the spectrograph again and again. They analyzed the data from every conceivable angle, searching for the mistake that would make the universe snap back into its familiar, comfortable shape. But the mistake wasn't there. The data was solid. The observation was real. The universe was not behaving as it should. This led her to a conclusion so profound, so radical, that it bordered on scientific heresy. The only way those outer stars could be moving so fast without flying off into the void was if they were being held in place by an enormous amount of gravity. A gravity far stronger than all the visible stars, gas, and dust could possibly generate. If you can't see the mass, but you can see its gravitational effect, then the mass must be invisible. It must be dark. Rubin realized she wasn't just looking at a galaxy. She was looking at the glowing tip of a cosmic iceberg. The visible part, the part we had studied for centuries, was just a tiny fraction of the whole. Surrounding it, engulfing it, was a colossal, invisible halo of something else. An immense amount of invisible, missing mass holding the entire structure together. Her calculations suggested this unseen substance wasn't just a little extra fluff. It was the dominant component. It implied that for every gram of matter we could see, there were 5, 6, maybe even 7 grams of matter that we couldn't. She had just discovered that 85% of the universe was missing.
Dark matter proof. One anomalous observation, even one as shocking as the rotation of the Andromeda Galaxy, is not enough to rewrite the laws of physics. In science, a single data point is a curiosity. A consistent pattern is a revolution. The initial reaction from the broader astronomical community to Vera Rubin's findings was, to put it mildly, skeptical. The idea of a universe dominated by an invisible, undetectable substance sounded more like science fiction than serious cosmology. Critics proposed alternative explanations. Perhaps Newton's laws of gravity, so reliable within our solar system, simply broke down over the vast distances of a galaxy. Maybe there was some unknown modification to gravity, a theory now known as MOND, that could explain the rapid rotation without resorting to invisible matter. Others suggested the observations could be explained by vast, dim clouds of interstellar gas or legions of faint, brown dwarf stars that simply hadn't been detected yet. The burden of proof was on Rubin, and it was an immense one. She had to show that this wasn't just a fluke in one galaxy, but a universal principle. So, she and Kent Ford embarked on a systematic, almost Herculean research program. They didn't just study one more galaxy, they studied dozens. They turned their telescopes to 60 spiral galaxies of different sizes, shapes, and orientations. From the majestic Messier 101 to the unassuming NGC 7541, they meticulously mapped the rotation curve of each one. And in every single case, the result was the same. The curve went up, and then it stayed flat. The problem wasn't unique to Andromeda. It was everywhere. This wasn't a single outlier. It was a universal pattern. This relentless accumulation of evidence was the core of her proof. It systematically dismantled the counterarguments. If it were just undetected gas or dim stars, you would expect the amount of missing mass to vary wildly and correlate with the visible features of the galaxy. It didn't. The effect was too large, too smooth, and too consistent. Her work also directly challenged the idea of modified gravity. While MOND could be tweaked to explain a single flat rotation curve, Rubin's data showed a rich diversity within that flatness. Some galaxies had slightly rising curves, others were perfectly flat, some had minor wiggles. Her precise, high-quality data provided a level of detail that simple modifications to gravity struggle to explain without becoming incredibly contrived. The simplest, most elegant explanation that fit the data was the existence of a massive, unseen component. Her data directly contradicted Newton's laws of gravity if only visible matter was considered. She wasn't breaking Newton's laws. She was revealing that we had only been applying them to a fraction of the total mass. The true power of Rubin's evidence was its simplicity and directness. She wasn't relying on complex theoretical models. She was presenting observational fact. Here is the light from the galaxy. Here is its measured velocity. The two do not match up. To reconcile them, you need more mass. It was this irrefutable observational foundation that slowly but surely won over the scientific community. While the Swiss astronomer Fritz Zwicky had first proposed something like dark matter back in the 1930s by observing the motion of entire galaxy clusters, his ideas were largely dismissed at the time due to imprecise data and his own combative personality. Rubin's work 40 years later was different. It was careful, methodical, and undeniable. She provided the smoking gun evidence that Zwicky's theoretical framework lacked. Her discovery fundamentally transformed cosmology. Before Rubin, astronomers were essentially cosmic cartographers, mapping the things they could see. After Rubin, they became cosmic detectives, searching for clues about a universe that was overwhelmingly invisible. The concept of a vast halo of non-luminous matter surrounding galaxies became a cornerstone of the new standard model of cosmology, known as the lambda cold dark matter model. This model, which now underpins almost all of modern cosmology, posits that the universe is made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. Without Rubin's flat rotation curves, this model and our entire modern understanding of how galaxies form and how the universe is structured simply would not exist. She didn't just find something new, she revealed the true stage on which the cosmic play is performed, a stage far larger and more mysterious than anyone had ever imagined.
Block 3. Nobel Prize Snub and Legacy. Vera Rubin's work provided the observational bedrock for one of the most profound shifts in human understanding of the cosmos. She empirically demonstrated that the universe we see is merely the foam on a vast, dark ocean. Her discovery kick-started a global, multi-billion-dollar effort to identify the nature of dark matter, a quest that continues to be one of the most pressing questions in all of science. Given the monumental scale of her contribution, the question that echoes through the halls of science is a persistent and troubling one. Why was she never awarded the Nobel Prize in Physics? She was nominated. Her work was widely cited and universally accepted as foundational. Yet, year after year, the call from Stockholm never came. When she passed away in 2016, the opportunity was lost forever, as the Nobel is not awarded posthumously. This omission is widely regarded as one of the most significant snubs in the history of the prize. The reasons are likely a complex mix of institutional tradition, scientific preference, and undeniable systemic bias. The Nobel Committee has historically shown a strong preference for discoveries in particle physics or theoretical breakthroughs over observational astronomy. They like to reward the discovery of a specific particle, like the Higgs boson, or a new fundamental theory. Rubin's work was observational. She didn't identify the dark matter particle itself, she proved it to exist through its gravitational effects. Some have argued that the committee was waiting for the direct detection of a dark matter particle, a discovery that has so far remained elusive. But this argument feels weak when you consider that Nobel Prizes have been awarded for the discovery of gravitational waves and the accelerating expansion of the universe. Both also inferred from their effects rather than a direct capture of the phenomenon itself. This is where the uncomfortable reality of historical bias comes into focus. Science, for much of the 20th century, was an institution built by and for men. Systemic biases that often overlook women in STEM are a well-documented part of this history. Vera Rubin herself faced immense barriers throughout her career.
She was the sole astronomy graduate from Vassar in 1948. She was barred from enrolling at Princeton's graduate astronomy program because they did not accept women. She had to fight for observing time at major observatories, which were often hostile environments for female scientists. The failure to award her the Nobel Prize feels to many like the final chapter in a long story of institutional gatekeeping. It's a painful reminder that even at the highest echelons of science, recognition is not always purely a function of merit. Despite her paradigm-shifting contributions, Vera Rubin was never awarded the Nobel Prize, a fact that stands as a stark indictment of the system itself. However, to define Vera Rubin's legacy by the prize she didn't win is to miss the point entirely. Her true legacy is not a medal in a Swedish museum. It is the universe itself, a cosmos she revealed to be far grander, stranger, and more mysterious than we ever knew. Her work is the foundation upon which entire fields of modern astrophysics and cosmology are built. Every experiment in a deep underground mine searching for WIMPs, every satellite mapping the cosmic microwave background, every supercomputer simulation of galaxy formation. They all stand on the shoulders of her meticulous observations of flat rotation curves. She fundamentally altered the questions we ask about the universe. Before her, we asked, "What is the universe made of?" and pointed to the periodic table. After her, we are forced to confront the humbling reality that 95% of the answer is still a complete mystery, filed under the placeholder names of dark matter and dark energy. Beyond her science, she was a fierce advocate and a mentor for women in astronomy, using her hard-won stature to open doors for the next generation. She championed the idea that there is no problem in science that can't be solved by a person, regardless of their gender. Her legacy is in the countless scientists she inspired, the questions she dared to ask, and the invisible universe she made visible to us all. Vera Rubin didn't need a Nobel Prize to validate her work. Her work validated a new model of the cosmos. She taught us that sometimes the most important discoveries aren't about finding a new star, but about recognizing the darkness that holds the stars in their place. Her work reminds us that the universe is full of secrets, waiting for a curious mind to look past the obvious and see what's truly there.